Hello, everyone. Welcome to another episode of CUDA Education. Today, I want to revisit a topic that I addressed in a previous episode, but I need to make a better version um, of said topic. Okay. Um, so first of all, we have two algorithms. We have actually let me do the bear with me. Let me do. So we have the compute n-body algorithm, where we simply have particles that are moving around with gravitational forces considerations between them. Okay. So we have these particles that are moving, and each particle is sort of aware of the number of particles around it, and the movement and velocity and position of the particle is affected by its environment, what's going on around it. Okay. Now, the topic of this conversation is the fact that this algorithm requires two compute passes. Okay. It requires two compute passes in order for the application to achieve what it needs to do. Okay. If we go to our compute particles, if we go to our compute particles algorithm, we only have one compute pass. Okay, so there isn't two compute passes. And what happens in this algorithm the um, is that the particles basically run independent of each other, right? There's no awareness in terms of calculations or anything of what's going on with other particles. Okay, so what you find is that there's only one compute pass with this algorithm, number one, and then number two, because you don't have to mathematically calculate any gravitational forces or consider particles around each particle. The computation for this algorithm is a lot less intense. It's more straightforward, right? So this algorithm only requires one compute pass. Okay. And I want to revisit this topic because I sort of mixed up the jargon, mixed up words. There is a thing called a compute pass, and then there's a thing called a render pass. Now, I know render pass is an official sort of it's an official term in Vulkan. Okay, it's an official term. Now, compute pass or simply the word pass isn't necessarily an official term. Okay, but they you know they, one sort of they both use the word pass, and that has some significance and is related in one way or the other. But a render pass generally means a render pass generally means graphics related it generally means graphics related stuff. Okay, so it's basically you're rendering stuff to the screen, and it is you're dealing with global render pass for frame buffer writes, right? You're dealing with um with with the graphics side of things, right? But what I'm addressing today is the compute um, is the compute pass, right? And we have two passes. We have the first pass here, and we have the second pass here. Okay. Now I'm in the compute n body, so just so we're on the same page, let me get back to compute n body. I'm on the compute n body algorithm. This is the compute n body algorithm again. It is computationally more expensive than the particles algorithm, right? And we have two passes. We have the first pass. Notice that it references a shader particle calculate .comp, which is these are the shaders for the default application, right? I hacked it and did some other stuff, but these are the shaders. These particle shaders are the ones that is with the application. So we have particle calculate, and this is the shader that deals with the this is the shader that deals with the forces vector, so the gravitational pull, push and pull of the calculation. It is where the heavy lifting happens, right? This is the more complex thing. So we have a first pass with with it being, so it's all of this right here, right? So all of this is the first pass, okay? And what happens, I'll just zoom in a little bit more so that you guys can see better. So we have our first pass, right? And it's basically with each of these passes, what we're trying to get to is we're creating a pipeline. VK create compute pipeline. Okay. So we have a first pass, we attach the shader for that pass, right? So what are we how are we what are we doing with this compute pass, right? um we attach a shader stage. Notice that it says VK stage compute bit, right? So we're attaching a shader to it, and then we do a bunch of stuff that naturally comes with creating a pipeline, right? And then we do VK create compute pipeline, and we have the handle for this, for the result of this function is compute pipeline calculate. Okay, so what generally defines you know first, one of the things that defines a pass, it's not the full thing, but I don't want to get to that yet. One of the things that defines a pass is that we create a pipeline with, we set up things to create a pipeline with vk create compute pipelines, right? um, and if we go to the definition for this, it's this guy right here, right? We have a device pipeline, all that stuff, right? So vk create, lowercase vk create pipelines, okay? So we have our first pipeline, right? And then we have our second pipeline. Now, the second pipeline, all that's doing is we have a particleintegrate.com, right? So all that we're doing with this pipeline, particleintegrate.com, right? All we're doing with this pipeline is we're updating the velocity and position of the particle, right? So particle calculate is figuring out what the gravitational forces are, and then particle integrate is updating the position and velocities, based on the knowledge of the gravitational force of the whole scene and everything that's going on. Okay. But this pass, this second pass, right? it it takes the results of the first pass, right? So the first pass does its thing, it does the calculations for each particle, um, taking into account the gravitational forces of things around it. And then the second pass, what that does is it takes the results of that first pass, and then it and gets the gravitational forces, the force vector is what they call it. And then they use that to update the velocity and position of each of the particles, right? So if we run our application again, we see that the particles move in a sort of a dance, right? And it is aware of what's around it, what's not around it, all that stuff. But you know the reason they move is that you need to have information of how many particles are around it, how many particles are not around it, and it does a thing based on the gravitational forces. So you have to calculate the gravitational forces, and then you have to update position and velocity so that the particles move the way they are, right? So the second pass does the actual update, but it's not as computationally intensive. Just a cursory look over the code. We're not going to get into the math. With a cursory look over the code, we see that um, basically, it's a lot less code, right? So this is a light, a lower, less intense on the CPU. So just like with the first pass, we set up a pipeline, and then the ultimate goal is to create this VK create compute pipelines. Okay, so for these passes, we are basically setting up a pipeline, a compute pipeline for each one. So we're setting up a pipeline for each one, right? So we have VK create compute pipelines for the first pass and VK compute pipelines for the second pass. Okay. Now the thing about it is that what sort of makes this process complete is that let's just deal with the pass itself. What makes this process complete is that we do VKCMD dispatch. Okay, so we do this VKCMD dispatch. Now this is in a different part of the code. Um, so this is in a different part of the code. This is in this is the build compute command buffer. Okay, so with that we do we do a VKCMD dispatch to for the pipeline calculate, right? So we bind first pass calculate particle movement, we bind it, we bind the pipeline, and then we do a VKCMD dispatch. Okay, so for the first pipeline, for the first pass, where it's a calculate particle movement, we do a VKCMD dispatch. Okay, for the second pipeline, we bind the pipeline and we also do a VKCMD dispatch. Now, VKCMD dispatch is basically now you're basically dispatching it to the GPU, and the GPU is actually doing the instructions. Remember, GPUs only follow um, they speak in command buffer language. So we created the pipeline sort of, all of this is this code and everything you see is, you know it's a CPU side, right? The literal GUI that we're using and everything is CPU side. But now we're dispatching the pipeline to the GPU, and we do that with VKCMD dispatch, right? That command inside of the command buffer. So, um, we basically started the command buffer, VK begin command buffer, right? This guy. We're starting the command buffer, and inside of the command buffer, we do our first pass and we do our second pass. Okay. Let's just look at the application just to take a little break. Okay. So here is our application. Okay. Now, what happens is that remember I said that the the first pass does the gravitational force calculations, and then the second pass consumes it in order to calculate position and velocity. All right. The thing about it is that you need to have a barrier. You need to have a barrier, which is this thing right here. Notice that it's between the first pass and the second pass. You need to have a barrier to make sure that when you're calculating and updating the buffer for the force vectors, when you're updating and calculating the buffer for the force vectors, when you're calculating and updating the force vector, you know, data and information and variables, that you're also not trying to read it at the same time. Okay, because remember, the second pass is reading the results of the first pass. So in order to manage that, to make sure you don't have race conditions, to make sure you don't have data corruption, to make sure you're not reading stale information and stale what have you, you basically you have to have a barrier between the two, so that when you're updating, you're not trying to read, and when you're reading, you're not trying to update at the same time, right? When you're updating, when you're calculating, you are blocking reads, and when you're reading, you're blocking calculations from happening and updating and changing the information, right? So in order to do that, you have basically a VKCMD pipeline barrier, and that's all of this guy right here. Okay, that's all of this guy, which I'm not gonna to get into. I've sort of gotten into it in previous videos, but I'm not going to dive into it too much. But basically, just understand that you have source mask, shader write bit, and destination mask, shader read bit. Add memory barrier to ensure that the computer shader has finished writing to the buffer, right? Transfer ownership if well, okay, yeah, that's if you have different family queues and queue families and all that stuff, right? But we have a VKCMD pipeline barrier that basically is sort of a division between the two to make sure that everything acts properly, okay? And then and that's sort of this is what you call a compute pass, okay? It's different from a render pass. A render pass deals with graphical stuff, and I do have a previous episode where I talk about the render pass specifically in this application, right? But we're not dealing with render pass right now. We're not dealing with render pass, aka graphical pass. We're dealing with the compute pass, which is updating and doing things, uh, updating, doing the computations, and then using the results of the computations to update what happens with the particles in this example. Okay. Now I do want to run an experiment, and I hope my video doesn't crash and everything doesn't go crazy. What I want to do is I want to just not update the second. I want to not do the VKCMD dispatch. So we're dispatching it now to the GPU. I want to see what happens if I don't do the dispatch for the second one. Will my application even run? Okay, it runs. But notice what happens now. We are doing calculations. We are doing calculations. I believe my I hear the fans on my machine. It's going fast. But notice that now we haven't dispatched the second where we're updating position and velocity. So we're doing the calculations. My machine is getting hot, the fan is going, but I don't visually see anything updated because the position and the velocities haven't changed, right? So that's pretty cool, and that's sort of what we expect, right? Um what happens if I don't even what happens if I don't do any calculations, but I do update position and velocity? Well, if I don't do any calculations, I believe I should see the same thing, right? Would you concur? I should see the same thing. So um we sort of see the same thing. We see oh, okay, I think I know what's happening here. So for the initial run, I believe the initial calculation is done on the CPU side. Okay, I think what happens is that basically every particle has a velocity with it, right? So for the initial run, I think it's CPU side. Every particle is assigned a velocity, so it's a position and also a velocity. So when we first run the application, we do have a position and velocity, right? So it starts out at a position, and then we have a velocity. The thing is that the velocity is the velocity. So the velocity, by definition, is a moving part, or it's a moving value, and it's going to the you could see the velocities changing. I mean, you could see the particle position changing because of the velocity. Okay, so the particles are changing because of the velocity variable that was initially calculated, I believe, on the CPU side, right? So there's initial calculation, and then the GPU takes over from that. But notice that um, the particles just keep moving. They don't. There is no. The particles are almost independent. They don't care about all the other particles around it. It's not changing direction or going out or coming back in or moving or whatever. The particles are just independently moving. Um, my CPU, my CPU and fan and everything is still loud, which is a little. I wasn't really expecting that because I haven't dispatched the first pass, right? So, well, anyway, I guess the second pass is still something, but yeah, notice that we don't have the gravitational forces or anything. So you start with a position and a velocity, and you just keep the velocity. Now, if I disable both dispatches, right? If I disable both dispatches, what I'm gonna get is what am I gonna get? What do you think I'm gonna get, guys? I'm gonna get a completely frozen thing. Remember, I said the yeah, we get a completely frozen thing, which I'm not too sure. That's something I have to investigate. We're not dispatching the first pass. We're not dispatching the second pass. Um, we do an initial calculation though. Um, it's completely frozen. That is interesting. It's completely frozen. I'll have to investigate why that is the case. But either way, guys, we understand that with a compute pass, you have to do you have to basically create the pipeline, and then in the command buffer, right? Remember, we're in the command buffer. We have to bind the pipeline, do whatever descriptor set stuff you need to do, and this then vk cmd dispatch, right? um, this is the guy that actually sends it to the GPU, and then the GPU can run with what needs to be done. This stuff is threads and workload and streaming multiprocessor calculations. I don't want to get into it right now because I want to just stay on the topic at hand. But VKCMD dispatch, if you guys want to, you could investigate it. You have group count X, group count Y, and group count Z. That's basically dealing with streaming multiprocessors and warps, and how many work groups you have, and just making sure that you're dividing up the bundles of work in proper order. Remember, each one of those particles have to run the shaders and all that stuff. So it's a lot of the number of particles is a lot, and you're dividing it by a specific amount of work groups and stuff like that. We're not going to get into that right now, right? But this is what a compute pass is, okay? Different from a render pass. Different from a render pass, okay? Now, compute pass isn't a term that's like an official thing in Vulkan world. Render pass is. Render pass deals with graphical stuff. um, compute pass is more just like, okay, we need to do two layers of computation. We need to make sure that there is a memory barrier between them so that they don't step on each other's toes, and we keep it moving. And let us just so where we created the pipeline was in, let's see what function, prepare compute, right? So in the prepare compute function, we created the pipelines in for the first pass and also for the second pass, okay? And then notice that let us so we have prepare compute, right? So prepare compute. Okay, so notice in our string of prepare, so we have a big prepare function. Notice that we call prepare compute, and where is prepare? So we call prepare compute. Um, okay. Right. So this creating pipeline is in the prepare compute function. Okay. And then in the command buffer is where we build com- build compute command buffer is where we actually consume those pipelines in order to get what we need. Okay. Now, continuing with the conversation, when we go to the particles, when we go to the particles application, which is this guy right here, again, we only need one computation. We don't need two, right? We just need one computation because now things are independent. We're not, the particles don't care about what's going on around it. It's just doing its own thing, right? So if we search for VKCMD dispatch, we'll see that um, sorry, I need to open up that file. Need to open up that file. Okay, so let's just clear out. So this is VKCMD dispatch, right? Notice that we only have one VKCMD dispatch inside of compute particles, right? Because we are just dealing with one computation, right? Um, Notice that we have particle.comp. So we just have one .comp shader thing that we have to deal with, right? Not two. So we still have to create a pipeline. vk create compute pipeline, right? Right? So we still have to create a vk create compute pipeline, right? We still have to create them, but it's just one, right? We still have to vk create a pipeline, and then VKCMD dispatch, right? VKCMD dispatch. So we have this whole concept was completely lost on me. Like I didn't fully grasp I didn't fully grasp the the whole idea of this thing, right? It just was lost on me. First of all, I was confusing. I was saying compute pass was the same as render pass. I was calling the compute passes render passes, which is not true. And I didn't fully appreciate the value of VKCMD dispatch, right? Which is different from VKCMD draw. Okay, so just like how in compute we have create the compute pipeline, VKCMD bind VKCMD bind pipeline, right? VKCMD bind pipeline, and then VKCMD dispatch for our compute passes. In the render pass world, we have VKCMD for instead of VKCMD dispatch, we have VKCMD draw. Okay, and VKCMD draw is basically it's basically what this dispatch VKCMD dispatch is for compute passes. VKCMD draw is for render passes, aka graphics passes, right? So you have compute passes and you have graphics passes. You have compute passes and you have render passes, right? Render pass slash graphics pass. It's the same thing. But naturally in graphics pass, you're talking about drawing. You're drawing things, right? So when you're dealing with drawing things now, we're talking about VKCMD draw, okay? And just like how we could disable dispatch. So let's actually disable the dispatch in the compute particles. Let's disable the dispatch. All right, so we're gonna disable the dispatch so that we basically don't do any we don't do any computations, right? There are no computations. We just have a screen of pictures. We don't do any computations whatsoever. Let's see if I could get one with the there's one where the color is just all the same. All right, but anyway, there are no computations happening, and that makes sense because we're not dispatching the computations to the GPU. Now when we put it back, Now we get our computations, right? Now we get our computations, right? Actually, we'll do it again just so we have. I don't know why the colors come on. Right. So we have computation now, right? Because we're dispatching it to the GPU. And I could pretty much bet that this is part of the command buffer, right? VKCMD dispatch. Build compute command buffer, right? So we understand that now. VKCMD dispatch. Okay, what I want to do is I want to disable it again, and I want to run it, and I want to see even with my attractor thing and the cursor thing, like nothing happens because nothing can happen because you can't do any, you can't submit any compute to the GPU. So let's just make sure that we're back to what we have before, and here we have our computes. Okay. So you guys fully understand that there is compute passes and there are render passes, okay? Um, just like as I said with dispatch, we also have dispatch for draw, right? So if we disable the draw, we basically don't draw anything, which basically leaves us with a blank screen, okay? So that is that for compute and render pass stuff. Um, do I want to get into anything else? I think that's it for today. That's it for today. So I apologize, guys. I did a previous episode where I talked about I mixed up the jargon and the terms, but just understand that um, yeah, render pass is a whole nother thing, right? Render pass is a whole nother thing, but there are compute passes and there are render passes. In order to do a compute pass, you need to basically create a pipeline, number one, create a pipeline, and then in the command buffer, you vkcmd the bind pipeline, and then you vkcmd dispatch the you dispatch the instructions to the GPU, right? That's what creates a compute pass. Okay, if you're dealing with a render pass, instead of VK dispatch, CMD dispatch, you do VK CMD draw. Okay? Now, real quick, there is also a version of this. There's also a VK CMD dispatch indirect. Okay? For those of you that remember, we had we talked about um, indirect rendering, where basically instead of submitting stuff from the CPU to the GPU, so you're doing a VKCMD dispatch. This command buffer is on the CPU and you're dispatching it over to the GPU. Instead of dispatching stuff from the CPU to the GPU, you could also dispatch stuff natively from the GPU. So this was the thing about indirect rendering. I have a whole series on indirect rendering. You could search my channel for indirect rendering and you will see the series that talks about indirect rendering. What indirect rendering was you're natively submitting new draw renders, or you're submitting new draw commands from the GPU. You're not going back to the CPU and then the CPU is submitting back to the GPU. You're natively submitting new draw calls from the GPU. Similarly, for that, I believe you also have the ability to natively submit new computation dispatches from the GPU itself. So you don't have that latency of going back to the CPU and then going to the GPU. You could natively do it on the GPU itself. Like if something changes, I know in the CUDA world, in the high performance computing world, where you're doing heavy calculations with CUDA, right, which is parallel processing and all that good stuff. That was one of the big innovations in CUDA was that if the calculations turned out that like you were going to go into a specific branch of calculations or a specific calculation tree, that instead of going back to the CPU and like waiting for another set of instructions based on the results, you just you natively like um you natively execute commands um from the GPU to the GPU, um, and process that new branch of information or that new calculations that need to be done. And what you do is you sidestep the latency between going back to the CPU and GPU, right? Remember, like this GPU stuff, a lot of it has to deal with speed, right? It's all about speed and efficiency, right? So you're doing calculations and you're also doing graphical stuff. So just like how we had indirect rendering for the draw stuff, you also have indirect. You could do a VKCMD dispatch, because you also have VKCMD draw in right. You also have VKCMD draw indirect, right? Which is which is the presentation version. So indirect rendering is VKCMD draw indirect. Uh, indirect computation is a VKCMD dispatch in indirect, right? But I mean, I'll have to do another video on that, and it's probably another episode, and it's probably I'm sure somewhere in these examples there's going to be an attempt to do an indirect computation. Okay, but hugely important thing. So you guys get a better grasp. There's compute passes and render passes. Render pass is the official term that's recognized by Vulkan and all that stuff. Compute passes, I don't know if they officially recognize that term, but you guys know what I mean when I say a compute pass now. And I totally screwed. I didn't even fully appreciate the VKCMD dispatch portion of this whole thing. Previously, it was just a big mess. But here I'm here to come to come full circle and just make it right. Um, so we have one VKCMD dispatch for this application, and in the compute n body VKCMD dispatch, we have we have two VKCMD dispatches, and you guys fully understand that because we're doing two compute passes. First, we have to calculate the force vectors, the gravitational pulls, or whatever, and then we have to update position and velocity. Okay, so that's that. I think this video is very valuable. You need to have a mental model of compute passes and render passes, and you also need to appreciate the fact that because you have two compute passes, you need to make sure you do some synchronization. So there is memory coherence. You avoid race conditions. You avoid data corruption. You avoid all of that stuff, right? One thing has to happen first and then the other, and the other can't happen without the first thing happening, while the first thing is happening, and the first thing can't happen while the second thing is happening, and the second thing can't happen while the first thing is happening. They have to be two separate things happening one at a time, right? Because we're organized here. So that's that for this video. Tutorial number 1 is installing the Vulkan SDK on a Windows-based machine with a Vulkan-capable GPU. Tutorial number 13 is installing all of these examples. If you want to be able to run the ray tracing examples, you need to also make sure that your GPU is ray tracing capable. Do your research before getting a computer. Very modern computers. I mean, like new computers that are like in 2026. They should be able to run on the integrated graphics card. So I actually have an NVIDIA GPU on my system, but just because, yeah. But I'm running on the integrated graphics card because it can process the it can process the it can process Vulkan on it, right? So I could do it on the integrated graphics card, which is sort of combined with the CPU, or I could do it on the NVIDIA graphics card. It's just that I generally do, yeah. But I just run with the integrated graphics card for now. But yeah, guys, get involved in this stuff. Time is expensive. Dedicate 2026 to learning, Vulkan. So by the end of the year, you could be proud of yourself and say, all right, I know a thing or two about Vulkan. You're not gonna know everything. I'm just warning you from now, but you're gonna be familiar with it, and it's not gonna scare you as much. Anyway, thank you for your time. Have a great day.